This is video 5.2, part 2. We're going to continue finding exact values using our sum and difference formulas. And towards the end, we're going to verify some identities, also using those formulas. Now, right now, we're going to start by taking a look at the tangent. So I have the tangent of 105 degrees. I want to see if I can rewrite 105 degrees as a sum or a difference of angles off my unit circle. I hope right now that you're thinking 60 plus 45 is 105 degrees. So let's just rewrite this as the tan of 60 degrees plus 45 degrees. If I add those together again, I get 105 degrees. I'm going to go ahead and use our tan sum formula. Now because we're adding, that means the sign in the numerator is going to be the plus, and the sign in the denominator is going to be the minus. So the first angle is going to be our alpha, the second one our beta. And let's go ahead and fill in what we know. We know tan of alpha is going to be tan of 60 degrees plus the tan of the other angle, 45 degrees, all over 1 minus the tan of 60 degrees times the tan of 45 degrees. Let's go ahead and use our unit circle and we'll find all those to plug them in. Now, off to the side here, just for a minute, I'm going to find the tan of 60 degrees. And that's going to be root 3 over 2 over 1/2. So that'll turn into root 3. The tan of 45 degrees is root 2 over 2 over root 2 over 2, which in fact simplifies to 1. Now that I know those, it'll make the rest of this process a lot easier. In place of tan of 60, I'll put root 3 plus 1 all over 1 minus root 3 times 1. I get root 3 plus 1 all over 1 minus root 3. And for what we need in this class, we'll leave it here as our final answer. Now, when you check these with the back of the book, you're going to not have the same answer because the back of the book is going to rationalize the denominator. And for what we need to do, we'll just leave it at that for this class. Let's take a look now at our next example. Now, the next example is going to get a little bit trickier. I'm going to be given what the sine of alpha is and also what the sine of beta is. And I want to find the cosine of those two angles and also their sums. So let's just go ahead and look at this first one. Sine alpha equals 4/5. Now it tells us that we're between pi over 2 and pi, which means that this angle is in quadrant 2. If I label my alpha in the inside, I know sine is opposite over hypotenuse. Now the nice thing with it being 4 and 5 is that this is a 3, 4, 5 right triangle. So I know that bottom is going to be negative 3. Let's do the same for the beta triangle. The beta triangle is between pi over 2 and 3 pi over 2. So it's down here in quadrant 3. And again, we're given sine opposite negative 2 root 5 over hypotenuse 5. We're going to have to do the Pythagorean theorem here to find our missing side. So let's put 2 root 5 squared plus our missing side squared equals 5 squared. Now negative 2 root 5 squared becomes 4 times 5, which is 20, plus x squared equals 25. So x squared equals 5. And when I take the square root, I get the square root of 5 as my adjacent side. It's going to be negative because we're going negative in the x direction. Now that I have my triangles, I can go ahead and find all the exact values below. The first one says to find the cosine alpha. So I'm going to go to the alpha triangle and I see cosine is negative 3/5. The next one is the cosine beta. So again, adjacent over hypotenuse, I get negative root 5 over 5. The next one's cosine alpha plus beta. Now, I'm going to have to use my answers from above to fill these in. Cosine alpha plus beta, if I remember the formula, means I'm going to have cosine alpha, cosine beta, minus sine alpha, sine beta. I'm going to need to plug in what I know and simplify from there. Cosine alpha is -3/5. Cosine beta, -√5/5. We found those above. Minus sine alpha, now that comes given in the beginning of the equation, 4/5. Sine beta, -2√5/5. If I do a little simplifying, I get, multiply on the top and the bottom, it looks like 3√5/25, plus 8√5/25, and that adds up to be 11√5/25. I want you to go ahead and do the same thing for part D, and we'll go over that one tomorrow in class. The last thing we're going to look at right now is establishing identities or verifying identities with these sum and difference formulas. So here's our example, and I'm going to go ahead and start on the left side of this identity. Now, in the numerator, I see the cosine of alpha minus beta. So I can go ahead and use my difference formula to rewrite that as cosine alpha, cosine beta, plus sine alpha, sine beta. And that's all going to be over sine alpha, sine beta. Now this is one of these where it's going to be useful to split up the fraction. So let's split up the numerator and leave the denominator. And I'm going to do the same thing on the other side. So you'll notice I split up the numerator, but I left the denominator. Now, if I look, cosine over sine I know is cotan, so I'm going to get a cosine alpha, and I'm also going to have a cotan beta there, because cosine over sine is cotan. So cotan alpha, cotan beta, plus, now all the signs here are going to cancel, so we get +1, and if you notice, that's exactly what I wanted it to equal. So just by splitting up that fraction and reducing a little bit, I was able to establish this identity. Let's take a look at another. On the left side, I see a tangent sum. So let's go ahead and use that tan sum formula. So we're going to get tan theta plus tan pi all over 1 minus tan theta times the tan of pi. Now, tangent of pi, I know tangent of pi. Tangent of pi, using my unit circle and the fact that it is y over x, the tangent of pi equals 0. So that means that this is going to be a 0 here, and so is this. Well, tan of theta plus 0 is just tan theta. Tan theta times 0 is 0, so we're going to get 1 minus 0. This is just tan theta over 1, which is tan theta. That's exactly what I wanted it to equal. So in this case, I actually had to find the tangent of pi and substitute that in.